probability of a type 1 error, where do I find beta? The probability of accepting a false null. Maybe down here, that's the truth. I was asleep late one night, I went to bed late and slept very soundly, and Tinkerbell came to me in my sleep and she told me that mu tilde is the truth. Well, even when mu tilde is the truth, the probability of rejecting the null is given mu tilde. Is that? And so the probability of accepting the false null, which we usually denote by beta, is there. Because if I didn't reject it, I must have accepted it. And we already learned that these things have to add to 1. So depending on where the truth is, although we get to pick a specific number for the probability of a type 1 error, depending on where the truth is, beta changes. The probability of a type 2 error is different. Just as to give you something to think about, we could draw a production possibilities frontier in the type 1, type 2 error plane. And our production possibilities frontier, given the geometry of probability functions, is going to be concave. And we always pick arbitrarily, like we we always seem to pick the probability of rejecting a true null to be a very small number, 1%, 5%, 10%, always. So that tells us something about our preferences. So folks must have indifference curves in the alpha-beta plane that are very steep because we choose alpha to be quite small. And once we know alpha, we can then talk about beta.
Just to frame this analogy a little bit farther, I guess the constant production in this situation would be the sample size, right? Because as you increase sample size, your alpha
you can change the shape of that by changing the sample size. Which raises an interesting question. As you read articles, journal articles in your discipline, accounting, finance, risk and insurance, or whatever, regardless of sample size, it seems that people always pick the same significance levels. Or if they're really schizophrenic for some reason, they put 1 star for significant at the 1% level, 2 stars for significant at the 5% level, and 3 stars for significant at the 10% level, or the other way around. So they're trying to cover all bases, right? But the choice of one of those 3 significance levels seems to be independent of sample size. I'm sure you can recall reading articles where the sample sizes are fairly small, and they use the same level of significance as the journal articles where they've got thousands of observations, and they're still reporting significance levels at 1, 5, and 10%, right? You haven't read enough journal articles to notice that. Could be. Anyway, you'll have to take my word for it, I guess. That's the way it is. In fact, if you're a student of statistical decision theory, you should be reducing the probability of rejecting a true null with the rise in the sample size. So that as your sample size grows to some of these intraday trading articles in the finance literature where they've got 10,000 observations on intraday trades over a 2-week period, the level of statistical significance in reporting their results should be vanishingly small. They should have a really stringent threshold that the statistical model has to jump over. But by and large, people don't do that. Okay. Mike Swartwood, what small sample test statistics do we use for hypothesis testing? Or which ones have you learned about thus far, and what did you use them for?
T-test, chi-squared,
and ratio of 2 chi-squares F. When do you use a Z or a T?
Z or T on the sample mean.
Right, when we're testing a hypothesis about the population mean, we usually use a Z or a T. Right. When you use chi-square? When you're testing a hypothesis about some parameter being estimated by a random variable that has a chi-square distribution. So what random variables do you know? Test statistics, sample statistics that might have a chi-square distribution. Remember, chi-square is the sum of squared normals. So what sample statistic are you in the habit of constructing that has squared terms in it? What sample statistic do you know of that has a chi-square distribution, has sums of squared terms in it? Suppose that you collected some data on, almost everybody in here is either wearing eyeglasses or contact lenses. And so you collected data on, numerical data on people's prescription. And you want to compute some sample statistics about the corrective powers of people's lenses. What sample statistics might you compute? Couldn't you compute the average correction strength of people's glasses? was a graduate student, I got a little consulting job, because in those bad old days, I wore contact lenses when I wasn't quite as blind as I am now. And I was having my contact lenses made by a really interesting optometrist. As a high school student and college student, I had a lot of trouble wearing contact lenses because my prescription was so thick that the thickness of the little tiny plastic lens irritated the inside of my eyelid. And so in college, I swam competitively, and the chlorine so corroded my eyelids and my eyeballs that I was then able to wear contact lenses in the water so long. But by the time I got to graduate school, I had not been in the water for a few years. And so it was a problem for me, and I had to have new lenses. So it turned out that this guy was working with an experimental contact lens maker in Chicago who said that if we knew the curvature of somebody's eyeball, their cornea, we could design the lens so that there was a little edge on it that picked up the tears in your eye and always caused it to float on a bed of tears over your cornea, and that would make them much more comfortable. So that their proposal was that if somebody's cornea looks like that, then the lens that we make for them ought to look like that. So you can see the little lip under the edge of the lens that would always cause it to float on there. But in order to do that, this segment right here has to have the same radius of curvature as the cornea, and the part in between has to be a little steeper, and then the little lips have to be a little flatter. Well, how do you do that? What's an isoquant? Anybody know? Explain to me an isoquant or an indifference curve quickly, or contour lines in a geographic map, or isoclines, or isobars. What's that whole idea about? Yes, where every measuring stays the same. So he understood this, and he developed an instrument so that he could take a picture of your cornea, and he could develop a topographic map of your cornea. But the trick, what he couldn't do, was getting from the topographic map back to the radii of curvature that you need to grind into the lenses in different places. So my consulting job was to create a little statistical model of the conversion from the topographic map to the radius of curvature that he had to have ground in these lenses. And then once he had the statistical model, he made a special slide rule so that he could just enter the contour contour map changes into his slide rule, and he could tell what radius of curvature to give to the lens grinding lab. Okay, so people do stuff like this. So they ask funny questions. Yeah, there's a camera. Can you take an overhead shot? Yeah, I don't know. You're probably too young, but in the bad old days, when people like me were young, one of the things that was very popular Christmas gift was a round disc with slides in it, little tiny transparencies. Yeah. And there were two tubes, and you put the little disc in the top, and you created these stereoscopic images. So what you do is you take the picture of the same thing from slightly different angles, and then you overlay them, and you have a three-dimensional image. And that's how he got from there to the topographic map. It's the same way they do geographic maps. They take it from two different angles, and that tells them how high off sea level it is. So you collected this data on the strength of people's prescriptions measured in diopters, and you want to summarize the thousands of data points that you got in some descriptive statistic. What kind of descriptive statistics might you want to compute? How about the sample mean? The average prescription strength of people's eyeglasses, right? You could compute that. And what's the distribution of the sample mean if you got a big sample? Yeah. You could also compute the sample variance. How do you construct the sample variance? Okay, so the sum of squared differences from the sample mean divided by n. That's the sample variance. She said that xi minus x bar squared added up over the index I. I live in a maximum likelihood world. Okay. So you could compute the sample variance. And what's the distribution of the sample variance? Chi-square, right? So you could use the chi-square distribution to test hypotheses about the population variance. Right? You can construct a test statistic which you know has a chi-square distribution and see whether or not you got an extreme value.